Hi everyone, I'm Pragnesh Patel. I'm currently a master's student at the University of Texas at Austin, and I'll be presenting our work on LogGen, a parameterized generator for designing floating point logarithm units for deep learning. The talk is divided into 6 parts. I'll start with providing a brief introduction and motivation behind our work, followed by a discussion of the past work. I will then describe the base architecture of our log unit and then move on to talking about the LogGen generator. Finally, I will discuss some of the results from our design space exploration using LogGen and the conclusion. So let's move on to the introduction. The motivation behind developing a floating point log unit was that a lot of applications like deep learning, image processing, digital signal processing, and bioinformatics rely on elementary functions like the logarithm. Complex arithmetic operations like multiplications, divisions, and reciprocals can be simplified by incorporating a logarithmic arithmetic circuit. We can also see that many deep learning algorithms use smaller floating point precisions instead of traditional floating point formats like single precision and double precision for computation. bfloat16 is a 16-bit truncated version of the single precision floating point data type used in Intel deep learning processors, FPGAs, and Google TPUs. TensorFloat32 is an emerging floating point data type that occupies 19 bits and is used in NVIDIA A100 GPUs. Also, efficient hardware implementation of deep neural network layers like softmax requires logarithm units of various fixed and floating point precisions. The precision used for deep learning algorithms impacts the hardware's area and performance metrics. A lower precision reduces the computational complexity and memory bandwidth required, but leads to a lower accuracy. They also decrease the training and inference time of deep neural networks. It has been shown that a lower internal computational accuracy does not lead to a significant overall accuracy loss in neural networks. This can be seen in Microsoft Brainwave's NPU architecture and NVIDIA Tensor Cores that were successfully able to use smaller precision floating point formats to achieve speed up with negligible impact on accuracy. Different accelerators require support for different formats and have different budgets for area, delay, memory, and latency. Also, different applications have different tolerance for classification accuracy. We have seen that some applications might even require logarithm computation for different bases. A one-size-fits-all design cannot satisfy all the requirements in such a diverse application space. Thus, we created LogGen to enable quick generation of log units based on the user requirements. We vary various aspects of a base architecture to generate these different designs. LogGen provides a valuable and convenient tool to explore the log unit design for different application scenarios and requirements. Currently, no such tool exists in the open source community. Let's now move on to discuss some of the past work on logarithm units. Based on our initial study, we found that the problem of implementing the logarithm function had been thoroughly explored. However, a lot of work has been focused on fixed point data types, traditional floating point data types like single and double precision, and parameterized log units. But no work specifically focuses on optimizing the designs for small floating point data types. There are several log unit options to choose from in both the industry and academia. There are certain proprietary IPs like the Synopsys DesignWare library and the Xilinx floating point operator that provide a parameterized logarithm unit. However, we show that these designs are very slow and require a lot of area. Moreover, the Xilinx floating point log operator only supports half, single, and double precision formats. We also saw that certain implementations use higher order approximations and Taylor series to design single precision logarithm units. However, using such techniques for small data types is inefficient in terms of resources and latency as it involves several floating point multiplications and additions. Moreover, Taylor series can only be used to calculate natural logarithm while our base architecture supports any arbitrary logarithm base. FloPoCo is an open source arithmetic code generator. However, there is a partial lack of compliance with the IEEE 754 standard. Based on our exploration, we also see that even the FloPoCo log units are more accurate. They're slower and larger in comparison to the LogGen designs. Similarly, Alakiotis proposed a log unit for single and double precision, His approach involves additional hardware units like subtractors, multiplexers, fixed to single precision data type conversion, and floating point multipliers that can be easily avoided for smaller data types using the table based approach that we use in our base architecture. Now I will discuss the base architecture of the logarithm unit used in LogGen. The formula that we use to calculate the logarithm of a number is shown here. A floating point number consists of three fields: the sign, the exponent, and the mantissa. Since the logarithm function is only defined for positive numbers, the sign bit can be ignored. We use the multiplicative property of logarithm to simplify this equation. This equation is used to compute the floating point logarithm function. A lookup table method is used to evaluate the terms, the left term and the right term in hardware. As shown in the previous slide, we'll need two lookup tables for evaluating the two terms of the equation and a floating point adder. We might also need an optional exception module to handle special cases. The LUT-EXP stores the pre-computed values of the multiplication between the exponent and the log of 2. This is possible since the log of 2 is a constant value. Hence, we can use the exponent bits to address the lookup table. For most floating point formats, the lookup table doesn't require a lot of memory. The LUT-MANT stores the pre-computed values of the log of the mantissa. We use the mantissa bits to address this lookup table. The LUT size increases exponentially as the mantissa width increases. We can see that while using this for a single precision format would require 256 megabits of memory, while half precision requires only 16 kilobits of memory. Hence, having a special lookup table for calculating the log of mantissa is only feasible for small floating point formats that are mainly used in deep learning applications. After fetching the outputs of the lookup tables, the final logarithm value is obtained by adding the two outputs. In our architecture, both 0 and subnormal inputs are mapped to negative infinity. If your application supports negative inputs, then the exception module can be added to map those inputs to not a number. This table illustrates the difference between memory requirements for half precision, bfloat 16 and TensorFloat 32 formats. We can see that half precision requires nearly 2.75 times the memory needed by bfloat 16 for the lookup tables, even though both formats are 16 bits wide. This shows that the architecture is most optimal for small mantissa and exponent widths. I will now discuss the structure and flow of the LogGen generator. There are 5 inputs to the generator that can be used to generate different log unit designs. They are precision, accuracy, base of logarithm, storage, and pipeline. The outputs for the generator are a bunch of Verilog files for the different log unit modules. There is also a makefile available in the repo that can be used to provide these knob inputs to the various scripts required for generating the log units. The structure of the generator is described in more detail in the paper. The precision knob defines the floating point data type supported by the generated design. Essentially, what this means is that using this knob, the user can input the exponent and mantissa widths of the floating point data type that they require. For example, if the input of the knob is 5 and 10, then the generator log unit will be for half precision data type. This knob only supports positive values as inputs. This knob controls the number of most significant bits of the mantissa used to index LUT-MANT. Thus, this knob essentially defines the LUT-MANT size and can be used to appropriately adapt the design based on different area and accuracy requirements of the user. Values that are less than or equal to the mantissa width of the precision knob will be considered as valid inputs. For example, if the accuracy is equal to 8, the first 8 bits from the MSB of the mantissa will be used to index the lookup table, even though the mantissa width for half precision data type is 10. So essentially, the last 2 bits are ignored. This knob defines the base of the logarithm function of the generated design. The base architecture that we have allows the flexibility to create log units for any arbitrary base, as the lookup table values are pre-computed and stored for any given base. All positive numbers are considered as valid inputs. The default value of this knob is E that generates a log unit to calculate the natural logarithm. However, other values like 2 or 10 can be also used to generate log units for log to the base 2 or log to the base 10 respectively. This knob can take 5 values and allows the user to choose how the lookup tables will be actually implemented in hardware. LG stands for lookup tables implemented using hard logic gates. This is optimal for small designs as for larger lookup tables, the area and combinational delay of the gates is very high. You can also use the synchronous single port read-write flip-flop based RAM provided by Synopsys or a hard macro RAM using the open source Open RAM tool. For FPGA designs, lookup tables can be implemented using the configurable logic blocks or the block ramps. The pipeline knob is used to choose between the different floating point adder implementations. Currently, we only provide this knob for ASIC designs, and there are two implementations to choose from. The first one is the floating point adder provided by Synopsys, and the other one is a custom design that has been designed by us. The Synopsys adder is actually highly accurate but has a large delay since it is not pipeline. Hence, we created a pipeline adder to achieve less delay, and however, it is slightly less accurate than the Synopsys adder. The choice of this knob can actually affect the area, delay, accuracy, and latency of the ASIC designs. We use the Xilinx floating point addition operator for the floating point addition operations for designs intended for FPGAs. I will now discuss some of the results from the design space exploration that we conducted using various log units created using LogGen. Due to the time constraint, I have selected a few interesting experiments to discuss in this talk. However, you can refer to the paper for more such experiments. For the FPGA evaluation, we use Xilinx Vivado for simulation and implementation. For the ASIC evaluation, Synopsys VCS was used for simulation and Synopsys Design Compiler was used for synthesis. The technology library that we use for synthesizing the designs is the free PDK45 library that uses a 45 nanometer ASIC process. For the accuracy assessment of the designs, the observed output values of the log units were compared to the expected output values from a Python-based CPU model for a large number of randomly generated inputs. One interesting experiment that we did was based on varying the accuracy knob. The orange line represents the average absolute error, while the green line represents the maximum error of the log units. The blue bars represent the area of the log units. We can see that as we decrease the LUT man size, both the errors increase and the lookup table area decreases exponentially. This is mainly because the size of the lookup table gets halved with every reduction in the mantissa bit width used to index the LUT mant. Upon examination, the design with accuracy knob 8 provides the best balance between the area and accuracy for half precision log units. There is only a slight increase in the average absolute error, while the total area nearly gets halved. Here, we compare the LogGen design for half precision with the scaled down architecture of the single precision natural logarithm unit from Alakiotis. The log unit architecture developed by Alakiotis was designed for single and double precision formats. Hence, the log unit was scaled down to half precision format using the same design blocks as our base LogGen unit. For a fair comparison with the half precision LogGen design, we keep the accuracy knob to the maximum value, that is 10, and use the same Synopsys floating point adder for both the designs. We can see that the LogGen design was nearly 1 times smaller than the scaled down version by Alakiotis. The frequency and latency are same because the Synopsys floating point adder is the critical path in the design. We also compared different ASIC designs like the Synopsys and FloPoCo log units with our LogGen designs. We can see that the Synopsys log unit has the lowest frequency among all the designs. Our optimized pipeline LogGen design had a frequency that was 6.1 times higher than the Synopsys log unit at the cost of just 1.2 times increase in the area. Our optimized unpipelined log unit is faster and consumes lesser area than the Synopsys log unit. However, it is less accurate. The FloPoCo log units are the most accurate among all the designs but also require the highest amount of area. We also compare different FPGA designs like the Xilinx IP and FloPoCo log units with our LogGen designs. It is to be noted that the Xilinx IP generator only supports traditional floating point formats for the log operator, while LogGen can support any arbitrary floating point formats. The Xilinx log unit is slightly more accurate but requires more FPGA resources than the LogGen design. Even though it can operate at a slightly higher frequency, it has a higher latency than the LogGen design. Also, FloPoCo is the slowest among all the three designs and also requires the highest amount of FPGA resources. Based on the design space exploration conducted, I will provide some concluding remarks. We have developed an open source generator called LogGen that can create log unit designs by varying five aspects: precision, accuracy, base of logarithm, storage, and pipeline of a flexible base architecture. The base architecture has been optimized for small floating point data types like half precision, bfloat 16, and TensorFloat 32. The LogGen designs can also be mapped to both ASIC and FPGA targets. The goal of LogGen is to enable quick evaluation of trade-offs between area, delay, latency, and accuracy of the log unit for the user. With new data types like TensorFloat 32 in NVIDIA GPUs and Microsoft Floating Point in Microsoft Brainwave constantly emerging and becoming increasingly popular in deep learning, LogGen can be useful to quickly generate efficient log units for these emerging data types. In addition to user-defined data type, LogGen can be used to generate log units for a user-defined logarithm base. As shown previously, the generated designs were compared to commercial open source IPs along with past implementations. Based on the comparisons, it can be concluded that LogGen designs are adequately accurate, and the area and delay metrics are as good as, if not better, compared to the other existing designs. Thank you everyone for listening to this talk. I'll be happy to answer any of your questions after this talk, or you can contact me via email.